Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're working examples using pressure vessels. This problem is a problem for Mechanics of Materials by Timothy Philpott, Wiley 3rd edition. The problem statement reads, when filled to capacity, the unpressurized storage tank shown in the figure contains water to a height of 30 feet. The outside diameter of the tank is 12 feet and the wall thickness is 0.375 inches. Determine the maximum normal stress and the absolute maximum shear stress on the outer surface of the tank at its base. So to summarize, we're asked to determine maximum normal stress, which is going to be the hoop stress. Find sigma hoop, as well as the maximum shear stress and tau max at the base. Okay? And it specifies at the base. Hopefully we can recognize, if we draw a little free body diagram of the tank here, we draw a little free body diagram, we can recognize that a tank filled with water is going to, up to a height of whatever the height is, okay, is going to induce increasing pressure on the tank, linearly distributed, that is going to be at a maximum at the base. So that's why we're asked to compute it at the base, because that's where the pressure due to the weight of the water acting on the tank is going to be the largest. Okay, so we need to recall what is the pressure of water acting over a certain height, and here the height h equals 30 feet. This is not something that we talked about in this class, but it's a very simple formula, and I'm sure you have seen it before, encountered it before. The formula is that the pressure is equal to the density times h. So at that location, at the base, we would use an h of 30 feet. So we can easily compute this, 62.4 pounds per cubic feet for the density times the 30 feet, and that computes to 1872 pounds per square foot. Okay? We're asked to find sigma hoop. Sigma hoop is equal to PR over T. Our P, 1872 pounds per square foot. My thickness is given in inches. I'm gonna convert this to pounds per square inch. So I recognize here I have a conversion factor of 1 foot squared divided by 12 inches squared to get this into pounds per square inch. Multiply by the radius. Okay, if the diameter of the tank is 12 feet, then the radius is going to be equal to 6 feet, which is 72 inches when we multiply it by 12. So times 72 inches, and then divided by the thickness, 0.375 inches. This is a very thin wall relative to the size of the tank, so really indicates how efficient tanks are in supporting large pressures. Okay, so finishing that up, that computes to 2496 psi, pounds per square inch, for the hoop stress. Okay, now the next part, we're asked to compute the maximum shear stress, and we want to consider this from a Mohr circle point of view. So let's write what we know so far. On the sigma and the tau axis, we have one principal stress, which is the hoop stress, over here at PR over 2T, or 2496 psi. Okay, the problem statement, which tells us that the tank is unpressurized. What that means is that there's not going to be any pressure acting upward. The only pressure is due to the water, and it's non-uniform. So we don't expect there to develop a longitudinal stress in the walls of the tank. In other words, the wall's longitudinal stress is going to be 0, and we'll have a second principal stress right here on 0. But it doesn't really matter. It's a plane stress situation, so we would have a principal stress here at 0 regardless. But now we know that the maximum shear is going to be determined in the plane of the walls. Okay, so our Mohr's circle looks like that. The maximum shear tau max is up at the top of the circle, equal to the radius of the circle, which is the diameter or the hoop stress divided by 2. So tau max equals 2496 divided by 2, which is 1248 psi. And that's it. So that completes this problem. It's a relatively simple problem that combines a few principles that you learned in other classes as well as what you learned in this class. That completes this example.